This video is to give you some hints or some things, ideas of things to try if you're stuck. Not going to work it out completely because this question doesn't regenerate, but I'm going to give you some help. So we're supposed to decide for what values of P this series converges. In order to do that, we're going to need to look at three different cases. So the first case we're going to consider, case 1, what if P equaled 1? So let's write out what that series looks like if P equals 1. So this would be just 1 over n to the 1, so we don't need to write the 1, natural log of n. Okay, to determine whether this series converges or diverges, we could use the integral test. Remember with the integral test that we can find the integral, and this would be from 2 to infinity, so it's an improper integral, so you'll want to set it up and then use the limit as b goes to infinity, but you're going to find the integral 1 over x, natural log of x dx. Not going to finish this, I'm going to let you, but you can compute this using u substitution, and then when you take the limit, as you go to infinity, if this integral approaches a single finite value, then you know that the integral converges, and so does the series converge. If this integral, as when you do the limit, goes to infinity, the integral diverges, and therefore so does the series by the integral test. Okay, so after you finish that, then you're going to need to do case 2. In case 2, we're going to consider what happens if P is less than 1. Now, to consider what happens if P is less than 1, let's figure out what n to the P and n, how they compare. We're going to try and figure out an inequality for this, and then we'll do reciprocals to figure that out, and then we'll get the natural log involved. So first of all, remember P is less than 1. So to be less than 1, it could be positive if it's between 0 and 1, so that would be some fraction, say like a half. And if it was a half, you'd have the square root of n comparing that to n, and the square root will be smaller. If it was a cube root, if it was, if you had 1/3 or whatever, if it's less than 1 but positive, you're going to be taking this root, and so it will be smaller. Now, if I made the inequality based on that, it would go this way. Now, would that still hold if P was less than 1 but was negative? So let's think, what if P was like -1? Well, if you wrote that without a negative exponent, that would be 1 over n, and n is just integers from 2 to infinity, so that would make that a fraction, so it would still be less. And if P was -2, same thing, because you could get rid of the negative. If P was a negative number, you could move that to the bottom of the fraction, and that 1 over n to the P is going to be less than n, then that's not a fraction. So this is the way the inequality goes anytime P is less than 1. So now let's take reciprocals, and remember when you do reciprocals, then you've got to turn the inequality sign the other way. So now we have 1 over n to the P is going to be greater than 1 over n. Now we're trying to get it to look like the series we're trying to test, so we're going to multiply each of those by the natural log of n. And so in doing so, we now have a comparison series for our original 1 over n to the P natural log of n, in our case where P is less than 1. Because this series on the right is the very thing you were doing right here. It's the case when P equal 1. So whatever you find in case 1, if you find convergence, then this series converges, and this other series is greater than it. So the inequality would be going the wrong way, but then you could do a limit comparison test. However, if in case 1 you found out it diverged, then this right-hand side diverges, and the one we're trying to test is greater than it, so it must diverge as well by the comparison test. So you're going to use a comparison test on this, either the straight up comparison test or the limit comparison test, to find out if case 2 converges or diverges. And now we've got case 3. And case 3 would be what's going to happen if p is greater than 1. So let's look at that. And if we have p greater than 1, let's write 1 over n to the p, and we're going to compare it over here, 1 over n to the p, and here I'm going to put a natural log of n so that it looks like what we're trying to test, and we'll see if we can figure out which way the inequality sign is going. For this problem, it says we're doing n equal 2 to infinity. The natural log of 2 is about 1.1, so it's greater than 1. And then, of course, if you did 3 and so forth, all of those are going to be larger still. So the smallest the ln n can be is about 1.1. Well, 1.1 is larger than 1, so if you multiply this denominator, the n to the p, by something that's larger than 1, it will make it bigger, larger. Well, larger denominator means smaller fraction. So we were figuring out which way the inequality goes, and it would have to go this way because we're multiplying that left-hand denominator by something greater than 1, making a larger denominator and therefore a smaller fraction. Okay, so with the inequality we have an inequality set up now, and we know over here what this side does because p is greater than 1. So it's a p-series with p greater than 1, and we've got an inequality there. So see how you can use that since you know that the one you're trying to test is always less than it. Again, it's a comparison test. After you get the 3 cases done, for each case you'll have an answer of converges or diverges. And then you're ready to answer this question that wants you to write an interval for what p could be so that it would converge. So if case 1, 2, and 3 all converged, you'd write negative infinity to infinity. If only case, say, 2 converged, then you would only write an inequality from negative infinity up to 1. If only case 3 converged, you'd write it from 1 to infinity, so forth. So figure out the convergence or divergence of each of the cases and then write an interval for p to cover all the times it would converge.